Okay, so before we begin going over the review, I want to take a second and make sure that you're aware of the outline, which is posted on the course website. So this is, as my disclaimer states, right? My disclaimer at the top in bright letter is that the only way to know what's actually on the test is to go to the outline and look at what's on the test. The review is just things that I think you might need a refresher on, okay? But you ultimately need to go to the outline, which is posted on the course webpage in the week 16 folder, I believe. And this is the outline of everything that is on the exam. So I wrote the test first and then made the outline from it. Physical and chemical properties and changes, chemical reactions, so write them, balance them. Empirical molecular formulas and percent composition, Lewis, Vesper, resonance, bonding type, so covalent versus ionic, and how do you know? Intermolecular forces, effects of those on physical properties, calorimetry, so we're talking about Hess's law, Q equals MC delta T, endothermic, exothermic, and Q equals NH fusion / vaporization. Yes. It's in the 30s. It's not that much longer than a regular test. If I didn't have the projector on, I'd pull it up and look, but got the projector on. I'll tell you at the end of class once I turn the projector off. Calculating protons, neutrons, electrons for ions, isotopes, and atoms, models of the atom, quantum theory, Bohr atom calculations, conservation of mass, stoichiometry, limiting reagent, redox, solution chemistry, functional groups, and gases. All right, so that is what's on the exam. And then again, this is already posted on the course webpage if you would like to see it. This is the reference page that you will be given on the test. So if you want to see what you'll be given, you can go download that off the course webpage as well. The solubility rules, a whole bunch of constants, your Vesper chart, heat capacities, periodic table, heat of fusion, vaporization, whole bunch of constants, all your formulas. So all of that is here. It's on the reference page, which is on the course website. All right, so like I said, this is my disclaimer. It's your responsibility to know what's on the outline. Just because it's not on here doesn't mean it's not on the test. Okay, this is just stuff that I think you could stand to have the review on. So let's go through these, each one of them, to make sure we're good on all this. All right, so write the electron configuration for barium using the shortcuts. Let's use this one. Knowledge on here. All right, barium, number 56, right? So what is our element that we put in brackets? We go up a row and to the end, so what is that? Xenon. And then all we're responsible for are the leftovers. So xenon 6s2. That's it. If I said write the full electron configuration, start writing, right? It's going to take a long time. But I specified using the shortcut. If I don't specify one way or the other, then you can choose either one. Okay? But if I specifically say giving me the long one, then I want to know the long one. So for instance, in number 2, I don't specify. I just say write the electron configurations. So that means you could go either way. You could pick either one you want. So nitride ion is nitrogen with what charge? N-3. So how many electrons does that have? Nitrogen is normally got 7 electrons. So nitride has how many? 10. So which element is it going to have the same electron configuration as? 7, 8, 9, 10. It's going to have the same electron configuration as what? Neon. All right, so 1s2, 2s2, 2p6, or you could have written that as helium, 2s2, 2p6.
Since it's neon, could you not technically just do brackets the neon?
Well, I really wouldn't tell you the electron configuration, though.
Sure. All right.
All right, let's do copper 2 ion. Copper 2 plus 2, right? So copper has 29 electrons. So how many electrons does copper 2 have? 27, right. So it's got the same electron configuration as who? Do you go up 2 or do you go down 2? Down 2. So it's got the same electron configuration as cobalt, right? So cobalt, let's just use the shortcut. Up and over would be argon. And then 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. Does everyone see how we got that?
Yes.
And then for oxide, what's the formula for oxide? Not peroxide, just oxide. O with what charge? 2 minus. So how many electrons does that have? Oxygen has 8, so oxide has 10. So it's the same as nitride, right? 1s2, 2s2, 2p6. Or you could have written that as 2s2, 2p6. What's the word we use when 2 elements have the same electron configuration? Do you remember that? Iso-electronic. Isotope, something different. Right? They have the same electron configuration, so they're called isoelectronic. Do we understand how to do these electron configurations? All right. Let's move right along then. Explain the difference between ions and isotopes. They both sound the same, well, sound similar, but they don't mean the same thing.
Ions have charge. Isotopes are changing the number of neutrons.
Okay, right. So what's the same about them, though? An atom versus an ion. Ions, same number of what as the atom it comes from? Protons, right? As the parent atom. Different number of electrons, right? And isotopes, same number of protons as parent, different number of neutrons. If you change the number of protons, can you still remain carbon, for instance, if you change the number of protons?
No.
No, right? That's like changing your social security number. If you change your social security number rather than committing fraud, you're also becoming a new person, right? In terms of your tax return, you're a new person, right? Versus changing electrons or changing neutrons, that's like gaining or losing weight, right? If you gain weight, you're still you, right? Whereas if you change your social security number, you're not you anymore. Okay, so changing ions, you can change the number of electrons, you can change the number of neutrons. That makes either an ion or an isotope. But if you change the number of protons, that's a new element altogether. Questions on this one? Definition, just a simple definition. All right, let's move on. Complete the orbital diagram for calcium ion. I kind of fleshed these out from the ones that were on your page, so it'd be easier for the projector to see it. Let's do both of these on the same page. All right. For calcium ion, what's the charge on calcium ion? It is Ca2 plus, right?
Yes.
Ca2 plus. So does that mean it's gained electrons or lost electrons?
Lost.
So it's lost 2, so it's got the same electron configuration as who? Argon, right?
Yes.
Calcium's got 20 electrons, so calcium ion's got 18. 18 electrons. It's isoelectronic with argon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Do you see how we did that one? Why does everybody see why it doesn't go all the way out to 4s2?
Yes.
Because it's calcium ion, means it's lost 2 electrons. And while we're on the topic of periodic table, let's pull this back over here. Well, let's fill in this chart. If you didn't know your symbol, you'd kind of be up the creek, right? Because your periodic table doesn't have the names. What is Mn? Manganese. How many protons does it have? Which number do you look at, top or bottom? Bottom number, right? 25. And how many neutrons does it have? How do you get that?
You subtract them.
Subtract, so how many?
30.
Just 30. Now, this is not Mn2 plus or anything like that, right? It's just regular old manganese. So how many electrons does it have?
25.
25. What if it happened to be Mn3 plus? How would you do that?
22.
You just subtract 3, right? And then hyphen notation, you write the name, and then a dash, and then what do you put? The mass number or the atomic number?
Mass.
The mass number, right. Think about why. Just always ask yourself why. Think about carbon. Carbon's got 4 isotopes. So it's got 4 isotopes. If you wrote the atomic number, what number would go here for all of them? It would just be 6. Could you tell the different isotopes from each other if you put the atomic number? No, it'd be impossible to, right? That's why you put the mass number. So you can differentiate between the different isotopes. So if you're stuck and you can't remember which one to put, just ask yourself, if I'm trying to distinguish isotopes, which one is going to allow me to do that? Because the atomic number would not allow you to distinguish isotopes, whereas the mass number would. Make sense? All right, let's do the next one. How do I know what element this is? Number of protons, right. What's number 50? 10. All right. Let's write our nuclear symbol first. 10, number 50's got a mass number. Let's just round to the nearest whole number. 119. Number 50. Sn. So how many neutrons does it have? We just subtract. 69. This is not an ion, right? It's not like it's Sn2 plus. So how many electrons does it have? 50. Again, if it was, say, Sn2 plus, you would what? Subtract. And then for hyphen notation, you would put 10 dash 50 or 10 119. 119. Because remember, if we had an isotope that was, say, 120, you'd need to be able to distinguish it. If it was just the atomic number, you'd never be able to tell them apart. Questions on 4 or 5, because they kind of go together, periodic table stuff. All right. Let's go on to the next part. Give myself a little bit more room here. So we're going to identify the orbital and draw them. And then we're also going to state the values of m sub L. If n equals 2 and L equals 2, what do we have?
Nothing.
Nothing does not exist. Why?
Because n minus 1 is the maximum for L.
L cannot exceed n minus 1. So nothing. What about for B?
Nothing.
Why? Why is the reason?
Well, because you can't have n equals 0.
N cannot equal 0, right? If I said draw a circle with a radius of 0, there you have it. Right? If I said draw a line 0 centimeters long, okay, there it is. Right? N is the radius. So you can't have a circle with a radius of 0. So n can never be 0. N equals 6 and L equals 0. What's that? Can you have L be 0?
Yes.
Yes. What is?
S orbital.
Okay. And what's the value in front? What's the number in front?
6.
6s. So if I said to draw that, how would you draw it?
A circle that has a radius.
Radius. 1, 2, 3, 4, 5, 6. Do the best you can. I'm not going to ask you to get out your compass. Just do the best you can. N equals 2, L equals 1. Does that exist? What?
Yes.
Yes, it does. What is that?
P orbital.
With what value of N?
2.
2p. So how would you draw a 2p orbital? What shape is that? You could draw it like a dumbbell. You could draw it like the figure 8. You could draw it side to side. The scale's kind of off there, right? There you go. There's your 2p. There's your 6s. Questions on number 6? Oh, we forgot the M sub L values. Thank you. Okay, for C, M sub L is what? 0. There's only one value of M sub L. What's the value of M sub L for D? There are 3.
-1, 3,
1. -1, 0, and 1. And what do those correspond to?
L.
The orientations, right? Because you could orient a p orbital along this one's oriented along the y, this x, or you could orient it along the z, right? So those are the 3 different orientations. Why is there only one value for a sphere? Does it matter which way you orient a sphere? It's going to look the same no matter how you orient it. Thank you. Okay, now we're ready to move off of 6. Yes. Let's move on to 7. List the possible values of M sub S. Let's just give ourselves a new page here. Produce a 4D orbital. All right. N, L, M sub L, M sub S. Let's refresh our memory. This is just the value in front. Let's make our little cheat sheet. 0, 1, 2, 3, S, P, E, F. How do we get M sub L? It ranges from what? Negative L to positive L. And what about M sub S?
It's plus or minus 1.
Plus or minus 1/2, right? Okay, so this is 4D. So all these sets are going to begin with 4. What's the value of L? 2. All right, let's go. I'm going to go negative to positive, so -2, and then positive 1/2. 4, 2, -2, -1/2. 4, 2, then what? -1, 1/2. 4, 2, -1, -1/2. 4, 2, then what? 0, 1/2. 4, 2, 0, -1/2. 4, 2, 1, 1/2. 4, 2, 1, -1/2. Last set, 4, 2, 2, 1/2. 4, 2, 2, -1/2. Do we see where these values came from?
Yes.
Any questions on number 7? All right. What if I just gave you a set and said, is this a valid set? Could you evaluate it and determine if it was valid or not? Just remember your rules here, right? The range of M sub L. What's the max value that L can be? N minus 1, right? So if I do happen to give you a set and ask you, is it valid? You can evaluate that. Okay. Let's just move this onto a new page too. Calculate the wavelength of light emitted when an electron falls from n equals 4 to n equals 2. So there is on your reference page the formula that you would use for this. This is the one we need. Negative 2.18 times 10 to the negative 18th joules. 1 over final minus 1 over initial, and square them both. So we have to calculate energy first, right? So energy is negative 2.18 times 10 to the negative 18th times 1 over final. Which one's the final? 2. So 2 squared is 4. And initial 1/16. So that gives me I got negative 4.0, let's just round, 9 times 10 to the negative 19 joules. Do we agree?
Yes.
Now that's energy. Let's look at our reference page. What do we need to do next? Because we want wavelength. Oops.
We gotta find the hertz of the situation.
So we have to find the frequency, right? How do we do that? This one, right?
Yes.
Planck's constant times frequency, and Planck's constant is on here. See, Planck's constant. Wait, is it? H, yeah. Okay, so now we need to find the frequency. So that's technical. Planck's constant times frequency. So we rearrange that. Frequency is just delta E divided by Planck's constant. Take our value, negative 4.09 times 10 to the negative 19 joules divided by 6.626 times 10 to the negative 34 joule seconds. Joules cancel, so we're left with units of seconds inverse, which is hertz. All right, so divided by 6.626 times 10 to the negative 34th. We drop the negative, right? Because can you have a negative frequency? No. So I got 6.17 times 10 to the 14th seconds inverse. Do we agree on that? But how do I get wavelength? Let's go check out our reference page. This is the exact reference page you'll have on the test. What do we need now to get?
C, fancy letter.
Right. So this is the relationship between wavelength and frequency equal to the speed of light. So C is equal to wavelength times frequency. C, what's that?
Speed of light.
That's just speed of light, right? So we're solving for wavelength. So wavelength is just speed of light divided by frequency. So 2.99 times 10 to the 8th meters per second divided by 6.17 times 10 to the 14th seconds inverse. Seconds go away. That's how we are left with units of meters. 2.99 times 10 to the 8th divided by 6.17 times 10 to the 14th. Gives me 4.85 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 meters, which will be 485 nanometers. Do we agree on how to do this? If you left it like this, by the way, that's fine. That's totally fine. That's just a unit you're more accustomed to seeing. But that's perfectly acceptable. Are we good on 8? Any questions about number 8? Okay, so that's a 3-step problem. All right. Let's move on to number 9. Naming compounds. Okay, what's the name of A?
Copper sulfide.
Close.
Copper 2 sulfide.
Copper 2 sulfide. Why do you need the 2?
So you know the electron configuration, so you balance equations.
Well, and you also remember, anytime you're in the transition metals, the D block, plus tin and lead, those need the Roman numeral because they can take on multiple charges. Good. MgO, what's that?
Magnesium oxide.
Good. How come you don't need?
Because magnesium is just a negative 2.
You need plus 2? Plus 2, yes.
Sure. Come on, man. I'll write it
Okay.
down right on the test, I promise.
That's all that matters. All right, PBBr2, what's that one? Do you need Roman numerals for PB?
Yes.
Yes.
Lead 2 bromide.
Lead 2 bromide. And then CuCl, what's that?
Copper 1 chloride.
Copper 1 chloride. Questions on 9. Spell check doesn't like those.
So if this was a case for, it may not be real, but if it's magnesium, then O sub 2, would it be magnesium dioxide? Is how you would write it? Or,
No,
okay, I'm not meaning just, I'm just meaning like as a general situation.
if it was 2 nonmetals, then you would use the prefix system, yes.
Okay.
So for instance, if you had, like, let's pick something, SeO2, that would be selenium dioxide.
Okay. So that's when I'm not.
There's 2 nonmetals, that's covalent bonding, yeah. And that's when you use your prefixes. All right, I'm trying to keep everything up so that if you're sitting in the back, you can see, okay? Right, formulas for these compounds. All right, calcium has what charge? Ca2+. Permanganate is,
-1.
what's the formula?
And then
MnO4 minus, yes. Let me give myself some room here because this is going to get crowded quickly. Yeah. All right, so what's the formula for this going to be? CaMnO4 2. Okay, this cobalt-3 tells me it's CO with what charge?
3+.
3+, and what's nitride?
N3-.
N3-, so this is just,
CO.
yep. Copper 2,
Cu2+.
Cu2+, what's hydroxide?
OH-.
OH-. I see this all the time. Is that acceptable? No, what's wrong? Use a parentheses where?
Around your OH.
Around the OH. Good. Okay, magnesium has what charge? Mg2+. What's chlorate?
ClO4.
ClO3-, right. So this would be MgClO3, what? 2. Okay, potassium has what charge?
1.
Okay, plus what's perchlorate?
ClO4.
Right, ClO4-. So this is just what? KClO4. All right, aluminum is what charge?
+3.
3+, and oxide is what minus?
2-.
2-, right. So this is Al2O3. Lithium has what charge?
1.
Plus, what's carbonate?
CO3, and then it's a 2 minus.
Right. So this is what? Li2CO3. Sodium has what charge?
+1.
Plus, and sulfate is,
-2.
what's the formula?
SO4.
SO4, right. So this is Na2SO4. What's ammonium?
NH4.
NH4 with what charge? Plus. And what's phosphate?
CO3-.
Close.
CO4-.
CO4, 3-, right? So this is NH4 3PO4. And then lithium is still Li+. What's nitrite?
NO2 with
So this is LiNO2. If you've forgotten your polyatomic ions, please break out your flashcards. Refresh your memory on polyatomic ions. They are definitely on the test. Questions on this one? Questions? All right. Let's go on then. What percent of ethane is carbon? How do you figure out a problem like this? Percent composition is How do you determine that?
You find the mass of carbon and put it over the mass of the entire.
Right. So this would be the molar mass of carbon in the molecule
Yes.
over the total molar mass, right?
Correct.
So times 100, yes. Okay, so for the total molar mass, 2 times 12.011 plus 1.008 times 6 gives me 30.07. And then 2 times 12.011. So 24.022 divided by 30. So that's 80%. Questions on how you do percent composition like that? What is the empirical formula of a compound? I'm just going to give myself home page for this one. What is the empirical formula of a compound that is 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen? What do you do?
Assume it's out of a 100-gram sample, so you can divide by the molar mass.
All right, so we're just going to drop all the percents and replace them with grams. So 71.65 grams chlorine, 24.27 grams carbon, and 4.07 grams hydrogen. And then we're going to convert them all to what?
Moles.
Moles. So 35.45 grams per mole, 12.011 grams per mole, and 1.008 grams per mole. So when we do that, 71.65 divided by 35.45. We're going to carry out lots of decimal places. 2.021 moles, 24.27 divided by 12.011. 2.021 and 4.07. That's got to be a wrong number. Chemistry, Laura Brook. Hey. Oh, yes, I will bring it down to you very shortly. Thanks. Bye. Actually, wasn't a wrong number. We used to get numbers for the bakery at the grocery store a lot, which I thought was funny. How can I help you? What kind of cake do you want? Okay, what do we do now?
I divide by the smallest.
Divide them all by the smallest number, so let's just round it to 2 because we all know what it's going to give us. 1, 1, 2. There's no 0.5 involved there, right? So if you were to happen to get a 0.5, what would you do?
Times 2.
You would double
Everything.
everybody, right? So this gives us an empirical formula of CH2Cl.
So if you wrote CCl,
It doesn't matter the order. Typically, you write the carbon first, and then the hydrogens, and then everybody else. But the order, I wouldn't mark you wrong. You wrote the order differently. Questions? Questions on 12? Questions on 12? All right. Let's move on then. 13, if the molecular formula of the compound in number 12 has a molar mass of 98.96 grams per mole, what's its molecular formula? So how do you convert empirical to molecular?
You find the empirical molar mass, and then you can divide the given molecular formula mass by the empirical and know how many times to multiply your empirical.
Right, so you just take the empirical and you multiply by some factor. Right? And that gives you molecular. So the factor that you multiply by is molar mass of molecular over the molar mass of the empirical. So this would have to be given, right? Because you wouldn't be able to do this otherwise. So 98.96. And then how do we get this?
You just calculate.
Right. The empirical is CH2Cl. So we just calculate its molar mass. So 12.011 plus 2.016 plus 35.45, 49.477. So 98.96 divided by 49.477 gives us 2, right on the money. So the molecular formula is just this times this. So C2H4Cl2. Do we agree on how to do this?
No, the molecular formula would have different properties than the empirical.
Oh, yes. Oh, yes. Definitely. This doesn't exist. There's no such thing as that.
Okay.
Right? That's just the lowest possible ratio. This is a molecule that does exist. Yes. Any other questions on this one? All right. And yes, the proportion would definitely change the physical and chemical properties. Okay. Let's see. We've got ourselves a solution stoichiometry sample on our hands. A 450 milliliter sample of 0.52 molar calcium chloride solution reacts with 125 milliliters of 0.78 molar potassium hydroxide. When mass of the product containing calcium is formed. All right, first thing we need is a what? Well, before we can do any of that, what do we need?
A balanced formula.
Right, balanced equation. So CaCl2 plus KOH. What's the product and also our precipitate?
CaOH2.
CaOH2, that's our precipitate, plus. Okay, so now we just need to do, is this a limiting reagent or is it just regular stoichiometry? This one's limiting reagent, right? Because we know information about both. So this is 0.45 liters and it's 0.52 molar, and this is 0.125 liters and it is 0.78 molar. We want to know what mass of this we can get. So we've got to do the calculations twice. All right, so to get moles, what do we do to get moles?
Molarity times liters.
Right, so 0.450 liters times 0.52 moles CaCl2 per liter. Let's just do this all as one because we're experts at this now, right? What's the mole ratio?
1 to 1.
1 to 1, right? 1 mole CaCl2. And if you still want to do it as 2 separate steps, that's totally fine.
We're experts though.
So that's where that comes from. And the molar mass of calcium hydroxide's what? 70 something?
74.094.
Sounds reasonable. Okay, so that goes away. So 0.45 times 0.52 times 74.094. So that's 17. How many sig figs we're keeping? 2. 17.3, blah, blah, blah. So that rounds to 17 grams. Are we done?
No.
Is that our answer? No, we got to do it twice, right? Because we have to see who's the limiting reagent. So you got to repeat that procedure. Molarity times volume. So the volume is 0.125 liters times 0.78 moles KOH per liter. Now the mole ratio here is 2 to 1, right? 2 moles KOH for every 1 mole CaOH2. This part's still the same. We don't have to calculate that again.
And you should get like 3.6.
So let's see. 0.125 times 0.78 times 74.094 divided by 2. I get 3.61 blah, blah, blah. Again, 2 sig figs, so 3.6 grams. So which one is our answer?
KOH.
The smaller number, right? KOH is the limiting reagent, and this is the theoretical yield. Is that a guarantee that when I go into the lab and do this, I'm going to actually come up with 3.6 grams? No. What's that dependent on?
Human error.
That's dependent on you, right? How good are you in the lab? This is what I'm supposed to get. Whether or not I get that because of my own abilities, that's a whole different story. That's when we calculate percent yield and percent error and all that good stuff. Questions on how we did 14? I know I went through it kind of quickly. Oops. Okay. Let's look at 15. Give ourselves a page break here. 2 grams of zinc metal reacts with 2.5 grams silver nitrate, so the 1 nitrate. Write the balanced chemical equation. The other product involves zinc 2, not zinc 1. All right, so balanced equation. What's the formula for zinc metal?
ZN.
It's just Zn, right? And silver 1 nitrate is what?
AgNO3.
NO3. All right, so what are we going to produce?
ZnNO3 2.
Mm-hmm.
And then Ag.
Plus what?
Ag.
Is that balanced?
No, it's 1, 2, 1, 2.
You 2 here, and you need a 2 there. Okay, now we're good to go. Theoretical yield is based on stoichiometry, right? So we've got 2 grams here and 2.5 grams here. And I want to know what's theoretical yield of this. So, is this a 1-step? No. This is a multi-step. Can I do it as one big long one? Are you okay with that? Or do you want to break it up into 3? Okay.
One big long.
Okay, so let's do zinc. 2.0 grams times zinc's molar mass is 65.37 grams per mole. Mole ratio is 1 to 2. 1 mole zinc for every 2 moles Ag. Molar mass of silver is 107.87. So when we do our arithmetic, multiply straight across and divide up. So 2 times 2 times 107.87 divided by 65.37. I get 6.60, because we can keep 3 sig figs. But I'm not finished, right, because I have to do the calculations again. So 2.50 grams. Let's calculate the molar mass of silver 1 nitrate quickly. I got 169.87. All right. So now the mole ratio here's 2 to 2, which is the same as 1 to 1. And then 107.87 grams per mole. Forgot to do this last time. Grams cancels, moles, zinc cancels, moles cancels. Here we go. Grams cancels, moles cancels, moles cancels. So now multiplying straight across and dividing up. So 2.5 times 107.87, right? Because 2 over 2 is 1, so that cancels. Divided by 169.87, I got 1.58, 1.59. So which is my theoretical yield? 1.59. And which is the limiting reagents? AgNO3. There was a question on one of the exams when I said, based on limiting reagents, if you just look at the initial amounts, that's the limiting reagent. Can you pick limiting reagent just based on the initial amounts? No, it's based on stoichiometry, it's based on mole ratios, it's based on molar masses, right? This one's smaller than this one, so if you didn't know anything about, I mean, this one's bigger. If you didn't know anything about stoichiometry, you just pick that, right? But now that you know stoichiometry, you know, no, you can't just look at the initial masses. It's based on mole ratios and molar mass. It's not how much you begin with initially. Questions on 15? I know I'm going through them kind of fast. I'm just trying to get through them all before we run out of time. Okay. The good news is the recording will be up this afternoon, so if you need to go back and see something again, you have that option. Okay, chemical reactions. We're doing some combustion. So that is a very specific type of reaction. What is, actually I probably want more space for each one of these. What is a combustion reaction? Okay, so it's C2H6 plus O2, and what are we producing? This is a hydrocarbon, CO2 and H2O. Will you get those same products if this is combustion of a metal?
Probably not.
No, because where would the carbon come from? Where would the hydrogen come from? Right, if this was aluminum right here, and you wrote CO2 plus H2O, that'd be garbage. Right, because where would the carbon come from? Where would the hydrogen come from? If this is aluminum right here, you just make aluminum oxide. Okay, so we've got to balance this. Want to just make a reactant product table? It's probably the easier way to do it, so you can do it in your head really well. So CHO, we've got 2, 6, 2. Write them in the same order on the other side. CHO, 1, 2, 2 plus 1. Why do we split this up?
Because they'll affect each other for which numbers you assign them to.
Right. If I put a coefficient here, it doesn't affect these oxygens. So let's balance carbon with a 2, distribute it. So 2 times 1 is 2, 2 times 2 is 4. And now let's balance hydrogen. So let's put a 3 here. 3 times 2 is 6, and 3 times 1 is 3. Okay, we've got a problem. Is 7 a multiple of 2?
No.
No, so what do I need to do?
Double it.
Well, if we use the fraction method, right, we say to ourselves, okay, 2x equals 7, so x must be 7/2. We put a coefficient here of 7/2. That gives me 7, and I'm balanced. But are you going to have 7/2 of an oxygen molecule?
Yeah.
No. So how do I get rid of that fraction?
Double it.
Multiply everybody by the denominator, right? So that gives me 2, 7, 4, and 6. And then if you want to go back through and recheck it with your table, it'll come out to balance. But you don't have to do that. If you did this part correctly, multiplying everything by 2 is not going to change. Are we good on this one?
Correct.
Combustion of ethane. All right. Now the nice thing about combustion is that the next one's a hydrocarbon too. So we're going to have the same products. We're just combusting a different hydrocarbon. I think it's octane, isn't it? All right, so it's different. C8H18. Let's make our table again. So carbon is C18. O is 2. Carbon here is 1. Hydrogen is 2. Oxygen is 2 plus 1. All right, let's balance carbon. So let's put an 8 here. So 8. 8 times 2 is 16. Let's balance hydrogen. So 9. 9 times 2 is 18. And 9 times 1 is 9. We've got 25 over here. Is 25 a multiple of 2? No, so we said to ourselves, okay, 2x is equal to 25, so x must be 25 halves. So if we put 25 halves here, 25 halves times 2 gives me 25. But is 25 halves going to happen out in the real world? No, so how do I get rid of that fraction?
Multiply by the
Multiply them all by the denominator. So that's 25, that's 2, 16, this is 18. How do we feel about this one?
easy.
Any questions about this one? Like I said, I know I'm going fast, but the recording will be up this afternoon, so if you want to go back and see anything, it'll be posted today. Last problem. What energy is associated with the n equals 3 energy level? If you didn't know this formula off the top of your head, you can look at your reference page. Which formula do you want to use?
Sub n.
Right, this one. E sub n is equal to this constant times 1 over n squared. So it's just negative 2.18 times 10 to the negative 18 joules over 3 squared. So when you do your math there, 2.18 times 10 to the negative 18 divided by 9, you get 2.42 times 10 to the negative 19 joules. How do you feel about 17? All right, questions about this packet as a whole. We've still got a few minutes left, so if you have a few questions, we could take those now. Any questions about this packet as a whole? All right, so tomorrow we're doing lab. Friday we're doing the last questions plus any questions you might have. So view that as an opportunity to ask any last minute questions. Otherwise, I will see you tomorrow.